Well, good afternoon, everybody, and welcome to our series on cathodic protection in hazardous environments. And I'm very happy to have with me one of my colleagues, Ruan Badenhorst, who is a cathodic protection engineer with SNET. Ruan has been involved in operation and maintenance of CP systems in hazardous environments for quite some time, and is going to, I hope, bring some practical insights to the discussion today. So this is the last section of our 6-session series on cathodic protection in hazardous environments. We've had a look at the definition of a hazardous environment. We've had a look at some of the challenges associated with implementing cathodic protection and some of the things we need to look at from a design point of view in coming up with a functional system that satisfies both the requirements for corrosion protection by means of cathodic protection and yet fulfills the safety requirements that are there from an electrical point of view. So Ruan, welcome to this session, and I'm looking forward to your input on the monitoring of cathodic protection systems in hazardous environments.
Yeah, thank you very much, Neil. Thank you, everyone.
So Ruan, what are the parameters that we generally look at when we're looking at whether or not a CP system is functioning, A, and B, whether it's functioning adequately in terms of providing protection to the infrastructure?
So, Neil, generally we monitor tank-to-swirl potentials as an indicator of protection. We also monitor the facility for stray current activity. This could be from incoming pipelines or railway lines in the vicinity of the site. And then we also inspect the electrical isolation typically found on the two stray current sources, as I've just mentioned.
Just starting with that, we spent some time earlier on in the series talking about the importance of electrical isolation, so I'll just pick up on that last point first. But do you find that the integrity of the electrical isolation is a challenge?
So generally the flanges are isolating adequately, but of concern is the lack of spark gaps at the majority of the sites, as well as the positioning of these insulating flange kits. For example, they are located at valves which require maintenance, and then some of the components are misplaced during this or not reinstalled correctly, or they could be missing an insulating washer or sleeve, and then the IF kit is not functioning as it's intended.
And what then is the effect of a malfunctioning flange?
The site would be then at risk at stray currents entering the site, and as we know, that's the whole purpose of the insulating flange.
In order to assess whether or not the stray current influences from outside are in fact affecting the site, how do you pick that up?
So generally we'll have some recordings that run overnight, and we'll put some data logging equipment on the incoming pipelines or the stray current sources, as well as the tanks, and then we'll have a look at whether any stray currents that pick up on the incoming pipelines or railways are reflected on the recordings that we see on the tanks.
With that information, what can one do about it? If you've got stray currents coming in, if you've got faulty insulating flanges, which are causing it, for example, then the influence of that is obviously that it may affect the level of protection in the tank farm. But what's the solution in that situation? How do we get the operators to sort out the challenges?
I think making them aware of the fact and maybe just reiterating the importance of these spark gaps and insulating flanges, and making sure that it's part of when if they're doing maintenance on valves on which the insulating flanges are installed, that it be replaced properly. I think awareness is the main thing.
The actual values then of the tank to soil potentials, how do we use those then in the evaluation of the integrity of the system on the site?
So we typically take two sets of measurements. So we take as found on potentials, which gives us an indication of the functionality of the system and can be an indication of the current distribution across the site. And then we take off potentials to determine the protection levels based on criteria typically used in the industry, like the -850 with respect to copper sulfate.
The term off potentials, does that mean that you switch the system off and then wander around taking readings, or how do you actually achieve, or how do you actually gather that information?
So off potentials are gained by what we interrupt the system. So we put a switch on the transformer rectifier unit and we just interrupt the power supply of current then to the tanks, and by that way we can get on potentials when the switch is closed, and then when the switch opens you can get what we deem instant off potential.
And those instant off potentials, then presumably the purpose of those is to get rid of the effects of the potential gradients associated with anodes. Last week we were talking about the location of anodes. Sometimes they're remote, sometimes they're close, sometimes they're distributed, and so on. So you can have situations then when you may or may not have significant potential gradients in the soil in the vicinity of the tanks where you're taking your readings.
Yes, so you'll see that off potentials are always less protected or less negative than the on potentials, and this is generally due to higher factors in the system. Then we've also experienced sometimes that you get higher on potentials at some structures or areas, which can indicate that a structure or an area is closer to anodes.
Okay. The potentials that you're taking, presumably you're wandering around the site now with a multimeter and a reference electrode. Where do you put the reference electrode? For example, if you're sitting in a facility where you've got a bund around the tanks, which is there to contain the product in case of a leaking tank, does that bund affect your readings?
Yes, so it is, we sometimes need to ensure, or we try to mitigate that. We try to take the measurement as close to the rim as possible, but it's important to note that this might not be an indication of the protection levels at the center of the tank. And Neil, you can maybe elaborate on the risks of corrosion still happening at the center.
As you rightly say, the potential that one takes when the reference electrode is close to the structure represents the potential of that structure in the immediate vicinity of the reference electrode. If you've got a 30-meter diameter tank, the potential at the rim may be very different to the potential at the center of the tank, particularly if your anode distribution is not optimum. That is, of course, one of the advantages of having remote anodes, is that you get better distribution across a large surface area. But as we discussed last week, the use of remote anodes is not always possible. And you have the challenge of current disappearing off into all sorts of other areas, particularly if you've got faulty insulating flanges. What other aspects of monitoring the parameters around the tank are relevant? If you're taking readings on a regular basis, what all can you deduce from those readings?
So historical trends are very important aspect when we're taking these measurements. So in terms of parameters, we try to decrease the number of parameters that can affect the readings so that we can get historical trends on tanks. So we typically try to take the readings at exactly the same spot, because as you said, the further away you are from the tank, it will already start affecting the readings. Obviously, this is one of the major reasons why we take instant off potentials, is to eliminate some of the parameters like the IR drop, as we mentioned, that can affect these readings.
Well, we've seen, not just in tank farms, but in many situations, that you get a significant change in the potentials that you measure depending on the location of the reference electrode. And of course, the closer you come to the structure, the greater that change is, or conversely, the closer you are to an anode, the greater the change relative to position. So how do you ensure that, let's say, if you were to go out to a site and take a set of readings, how do you ensure that the next person that goes, who may not have been with you the first time round, takes the readings in the same spot so that your readings are consistent from survey to survey?
So, Neil, typically we try to take the potentials at the cardinal points of a tank, so on the north, east, southern, and western points of the tank. This is not always practical or not the best way to do it, because as you said earlier, you were talking about a 30-meter tank, so we get tanks that go up to 50 meters. Now, north for me and north for the next person can differ by a couple of meters, and all of that can make a difference in the readings. I mean, 5 meters more clockwise and 5 meters more anti-clockwise can certainly affect the readings, because you might be closer to an anode. So we typically try to take it, like I said, on north, east, southwest, but the best way to do is if there's a dedicated monitoring point. So sometimes there's a stud welded onto those points, which then ensure that the next team will always take it on the same position. And then you also get what we call monitoring tubes, which is then a fixed position where we can take readings every time.
And those monitoring tubes, are they then installed through the floor of the bund? I mean, not all sites have bunded areas. Sometimes you just have ordinary ground, in which case that's obviously not a problem. It's just a fixed location. But in a bunded area, that monitoring tube, doesn't it compromise the integrity of the bund from an environmental leak point of view?
So even though the pipe will protrude through the concrete, it is adequately covered up. So the hole in which you drill through the concrete and the PVC pipe will be very similar to each other, leaving a very small annulus around the pipe, which is then grouted. And then the monitoring tubes are filled with a bentonite sand mix. And as we know, that bentonite is very good at retaining any moisture. Mm-hmm. And then we top it off by using an end cap, which is screwed onto the monitoring tube, which prevents any ingress.
So those monitoring tubes actually then represent very little risk in terms of compromising the integrity of the bund. I mean, we've seen many situations where you've got earth rods and odd bits of foundation and concrete joints which are not sealed and things like that, which would possibly represent a bigger risk.
Yes, certainly. I think it's as much as a risk as any other penetration through the bund, be it through earthing spikes or other services. So I wouldn't say that it's any greater risk than any of those.
No. And Ron, what is the situation then with the other alternative? I mean, you've spoken about the importance of having a fixed point in order to ensure that you get consistent readings. But what would happen if you were to use a fixed reference electrode, or as in the industry, they sometimes refer to them as permanent reference electrodes. I don't like that particular designation because nothing's permanent, but a stationary reference electrode. What's the practicality of doing something like that?
So under-tank electrodes are certainly beneficial, but they're not always considered during the construction of tanks, and therefore make it slightly more complicated later on. It's also important to remember that these SREs tend to drift, as you just mentioned, and they may need to be calibrated from time to time to ensure that accurate readings are obtained. And then it's also important to note that you get different types of stationary reference electrodes. You can typically use zinc or copper sulfate stationary reference electrodes. But it's also important to remember that there's a potential difference when measuring with these two reference electrodes. For example, we use negative 850 millivolt to negative 1150 millivolt when using copper sulfate to determine protection, but we use positive 250 millivolts to negative 50 millivolts when using zinc. So there's a significant difference, and it can easily give the impression that a system is not protected when thinking the potential is measured with respect to copper sulfate, when in fact it's a zinc reference electrode and it could actually be protected. This is also helped greatly with remote monitoring. We use remote monitoring to remote the functionality of the system by evaluating voltage, current, and reference potential. So Neil, you can maybe talk about the advantages of remote monitoring in hazardous environments.
There, of course, the benefit is that you don't need to draw a permit and physically go wandering around the site, particularly as a lot of the monitoring equipment that we use is not intrinsically safe. And therefore, the permitting situation means you've got to have a hot work permit because you're now carrying a battery-operated device. And that certainly complicates the monitoring aspect. And of course, hazardous environments are not just hazardous from a fire risk point of view. There are things like bulk sulfuric acid storage tanks, where you've got a 30-meter diameter steel storage tank filled with concentrated sulfuric acid. And the operators get very excited about people wandering around inside those bunded areas just from a risk point of view in terms of the personnel. Because if something happened whilst somebody was physically inside the bund, they would be toast, quite literally, if they got doused in acid. And I know from some experience I had on some bulk storage tanks that fortunately nothing ever went wrong, but everybody was on tenterhooks when there were people walking around inside the bunded area with a tank full of acid on the other side of the steel wall. And Ruan, you mentioned that the challenge that we have in terms of reference electrodes drifting. What other means have we got of establishing levels of protection if you don't have full confidence, let's put it that way, in your reference electrodes?
So there's another method which is the 100 millivolt decay or depolarization test that we can do. Before you can do the test, it should be noted that it takes time for a system to polarize. So it can't be done very close to installation, for example. I know we usually require a minimum of 30 days before we can even think about doing the test. And the system needs to be on 100%. We need to have 100% on time for that to work. We had quite a struggle during the times of load shedding. Now there's a bit in the past now, but in the times of load shedding, it was an issue because systems weren't 100% on, and that affects the polarization. And then secondly, I would say the downside of this survey is that it takes time to complete. An instant off survey is something that can happen immediately. Well, when you reach the site, you can do your test. But with 100 millivolt decay, you need a couple of hours, 24 hours, and even more is an advantage.
The 100 millivolt decay survey, is that a common system, or is it something that you do when perhaps one of the more conventional surveys brings the level of protection into doubt?
So generally we use an instant off survey, as you said, but the preferred method for bare steel is a 100 millivolt decay survey. But as I said, it takes time. So generally when you do some level of protection surveys, we do 850, but the 100 millivolt decay survey can be a good indication then, or a secondary test when the site does not pass the 850 criterion. The 100 millivolt decay is certainly a second survey that you can do to confirm protection on a site.
Yeah, I would imagine that there must be many sites where the significant surface area of the bare steel related to the tanks actually results in levels of protection that don't meet the 850 millivolt off for copper sulfate. If you were going onto a site and you had action records, how on earth would you know whether, say you were given a set of readings from somebody that had taken them off a remote monitoring system or something like that? How would you know whether your reference electrodes are zinc or copper sulfate, or maybe there might even be silver chloride if you were in a coastal environment?
So it is a challenge, especially with historical documents on cathodic protection installation, and especially with stationary reference electrodes. You also get sites where there's a mixture of the type of reference electrodes. You might get two tanks right next to each other, each with their own, one with copper sulfate stationary reference electrode, and the other one with zinc. The best is to test. Neil, you would use a portable reference electrode, and you can then check as we mentioned, you can only get to the rim of the tank, but some of the tanks have stationary reference electrodes that are at intervals, so you get one in the center, mid-center, and then at the edge. You'll typically try to take the one closest and then measure it with respect to a portable reference electrode, and that could be a good way to determine what you're dealing with.
So that is effectively operating as a field calibration exercise, because obviously you know what the portable reference electrode is, and you can determine what the equivalent potential of your stationary reference electrodes is. And I suppose that also then is a major advantage of the 100 millivolt decay test, is that you don't have to have the absolute value of the potential, because it is the change in potential that is indicating the level of protection.
Yes, that's correct. That the 100 millivolt completely take out the conversion factor that you need to do, or no need for guessing when using the 100 millivolts. As you said, it's just a difference in potential rather than an actual potential that you're following because of a criterion.
And then, Ruan, from the records that you get from monitoring, you mentioned the importance of maintaining records so that you can tell whether something is changing. What are the changes that you might pick up from long-term record keeping?
So typically, a lot of the sites have tap change rectifiers, which is constant voltage. So your voltage is not really an indicator of anything changing, but typically your current is a good indicator of a system changing. You might get a drop in current due to anodes depleting, or it could be due to seasonal variance. And the same effect can then be seen on the reference potentials. The potentials might be less negative, as maybe during dry seasons. Again, seasonal variance play a big role. The wetter it is, the better it is for CP. So current and reference potentials are both very big indicators of a system's functionality.
So from that point of view, trend analysis is a vital thing, because you can't determine a trend if you only have 2 points. You need multiple points over a period of time. And I presume then that if we have that sort of data, we can use that in maintenance planning.
Yes, that's true, and that also highlights the importance of regular surveys. If you're having surveys at exactly the same time once a year, you might not get an idea of what happens at another time during the year when it's drier or wetter.
Well, that leads us into the subject of planned maintenance, where we can use our cathodic protection parameters to good advantage in that planning. And that's going to be the subject of our discussion tomorrow, when we talk about planning and some of the other benefits that you can get from having an operational cathodic protection system in your hazardous environment. So, Ruan, thank you for your input today.
Thanks, Neil. Yeah, looking forward to tomorrow's session.